if you want the current, if you want to generate a PTAT current, right, what happens eventually, as we saw, VBE1 must be equal to VBEN plus IR, correct. So, one way of finding that magic current VT ln N by R is to force the same current, okay. So, this is basically saying the voltage across this branch. Remember that VBE1 is the voltage developed across the diode when the current is I, the same current I is flowing through both branches, correct. So, if the voltage across both these branches is the same, when you pump the same current, the resulting current is PTAT, correct. So, these two branches must have the same current flowing and the same voltage across them. So, one way of getting at that magic current is therefore to pump some arbitrary current, right, and look at the two voltages and tweak the current in the right direction until the voltages are the same, because eventually the voltages must be the same, the currents must be the same. Okay. Now, can we think of an alternative way of getting at the same principle? We pumped the same current and were looking at the voltages. What else can we do? What else can we do? So, basically the other the obvious extension of this approach is to say, well, I will apply the same voltage across both the branches. In general, what comment can we make about the currents? If I apply the same voltage across both these branches, in general, for an arbitrary voltage, what comment can we make about the two currents? They will be different. But for some magic value of the voltage that you apply, the currents will be the same, right. That is that current that results is I star. Is that clear? Okay. So, this is the principle. Now, I mean, we can cook up a circuit to do that. So, you want to apply a voltage and measure the current. So, what kind of control source do you think we want? You want to apply a voltage and measure the current. What kind of control source does this take? Voltage controlled current source. So, what is the simplest voltage controlled current source topology that you know? Single transistor voltage controlled current source. Pardon? Okay. So, basically, so I have applied a voltage here. Okay. And what is the voltage? If I apply a Vg here, what is the voltage at this? What is the actual voltage across these two branches? What is the voltage here? What is it in terms of Vg, man? Vg minus Vt minus delta V. That delta V depends on the current flowing. If you want the delta V to be independent of the current flowing, what should we do to the size of the transistors? Make it infinite. So, then what comment can we make about the voltage at the source? It is Vg minus Vt, where Vt, this Vt is not to be confused with the Kt ln Q, I mean sorry, Kt by Q. Is this clear? Okay. So, do you agree that now the voltage across both the branches is, what comment can we make about the voltage across both the branches? It is the same, correct. So in general, this current, what comment can you make about I1 versus I2? In general, what comment can we make about I1 and I2? They will be different, right? So what is our experiment? What should we do in the lab? We should go on changing Vg and keep comparing I1 and I2 and change Vg in the right direction. Does it make sense? Alright. So to figure out what the right direction is, we know that for Vg is that magic Vg star, I1 and I2 will be identical. For Vg much smaller than the magic voltage, correct? Which current do you think will be larger? Let us say when Vg is much smaller than Vg star, what comment can you make about the currents I1 and I mean, what comment can you make about the magnitudes of the currents? If the currents are very small or the currents are very large? The currents are very small. Okay, for very small current, what comment can you make about the drop of the across the resistor versus the drop across the diode? The diode, which one can we neglect? We can neglect the drop across R. Okay, so for very small Vg, right, the entire voltage that you apply is appearing in this case across a diode of size N, whereas here it is appearing across a diode of size 1. So which will have more current? N. It will have N times larger current, correct. So for Vg less than Vg star, I2 will be greater than I1. It will be N times larger, and because of the exponential characteristic of the diode, for small Vg, both of them will have an exponential characteristic, correct, and the ratio of the two will be I1 to I2 will be N, right. Now as the voltage Vg keeps increasing, what comment can you make about I2? Which voltage drop can you neglect as I becomes more and more? The diode drop will change very little because the voltage is logarithmic, whereas the voltage drop across R is linear, right. So eventually which was something which is going exponentially will only go linearly like that. I mean, I think I am a bad artist, but okay, it will go linearly, whereas this is the I2 must basically do this and eventually go only linearly. What about I1? I1, this is I2, I1 will basically go, just simply keep going exponentially for all values of Vg, right. So this is I1, correct. So for the magic value of Vg star, both the currents will be the same. Let me call that I star. And what is so special about I star? I star is a PTAT. Alright. So basically it's saying that if I2 is greater than I1, means Vg is less than Vg star, so must increase Vg. Alright. So how do you make, so you have to compare I2 and I1 and change the direction of Vg in the right way. How do you compare? What physical principle will be used to compare two currents? KCL. So and comparison is difference. So I need to basically, if I want to compare, So if I somehow make a copy of I2, all right, okay. If I2 is greater than I1, what comment can we make about node X? So if I2 is greater than I1, which means Vx goes up, all right. So if Vx goes up, Vg must go up, okay. So basically what must we do? Connect it this way, okay, fine. Now the question is, the only the only problem now is, how do I generate a copy of, how do I make, I have I2 here on the right side, how do I make a copy PMOS current? Where must I put the, which of the devices on top will be diode connected? Right, because I am copying I2 and making, all right. Understand? All right. So what is the only problematic part in this circuit? Infinite transistor. So is it really now a problem? What is the current flowing through both these transistors? Let's call them M1, M2, M3 and M4. M1 and M2, both the transistors carry the same current. So so should we be so is it necessary that the voltage the size be infinite? Why? The overdrive is the same, right? So basically you don't need the infinite size after all, right? Even with the finite size, you will basically end up with the same voltage. If you apply a voltage at the gate, you must get the same voltage at both source on both sides, and once the circuit is stabilized, that's what happens anyway. Both currents are the same, so the voltages across this branch and this branch are the same. Does it make sense? Okay. Deceptively looking, I mean, and of course, if you have never seen the circuit before, the analysis is pretty straightforward. I mean, so in other words, I mean, all I'm saying is that instead of wasting so much time, deriving the circuit from scratch, you can as well show the final circuit and say, well, if you look at the circuit, how do you analyze it? Well, that's easy. Oh, well, this is I, right? Or the same current must flow here. So this is I, and therefore the voltage drop there, you write KCL in this loop, and then, well, VB1 minus VBN equals IR. So I mean, it's obvious that the current I is VT ln N by R. Okay, but the problem comes if you don't understand carefully. Now, let's say I gave you this circuit like this, okay, and if you didn't know anything, you would just still complete this again. You would go through the, I mean, the equations are still the same current flows. If, I mean, you assume this is I and this is I, and yeah, you apply KVL across the same loop. So it appears as if it makes no difference whether it was whether you mirror this way or you mirror that way. It turns out that if you analyze it carefully, it turns out that this way of doing it is basically positive feedback, right? It is like saying, if you didn't know anything about negative feedback and you thought always that the virtual ground of an op amp is a short no matter what, then what would you wonder? Now, why is all this fuss about this plus and minus and so on? The signs, I mean, anyway, it's virtual ground. So, what happens if I flip the signs at the input of the op amp? You would think that, you know, if you just mug up the rules for the op amp, I mean, you would wonder whether, you know, why are we, why are we being so fussy about the signs of the op amp, right? So, this is basically the same thing, right? So, so the correct signs are this one. Okay. Now, all these circuits that we have seen so far, this is one equilibrium point, right? Now, the zero current state is also an equilibrium, is a potential operating point. Okay. Remember that the voltage VB1 is VT ln I over IS only if I is much larger than IS, right. So, but the true equation is 1 plus ln of 1 plus I by IS. So, for example, in this circuit, if all the currents were, if the currents were 0, what is the voltage drop across this diode? 0. What is the voltage drop across that branch? 0. So, the voltage across this branch of both branches is the same. The currents through both branches are also the same. So, it evidently it is that's a possible operating point, right. Fortunately, it turns out that it is an unstable operating point, and if you actually slightly kick one side, it will come to the desired operating point. But when you are trying to make a product, you're not, I mean, you shouldn't be praying that something happens. Okay. So, usually, I mean, so basically there is it's straightforward to basically, if you know that the current flowing through any of these transistors is 0, right, you know that there is the circuit is stuck at that all 0 state. So, it's a simple straightforward matter to simply detect if no current is flowing and go and kick any one of those nodes and push it out of that unstable operating. So, these are all called startup circuits. I am not going to cover it in this course. You will see it in analog IC design when you do it next semester. So, likewise for this also, here also the 0 current state is a stable operating point, right, and likewise here. Okay. So, I mean, and you can see that the basic principles are, I mean, after all, the basic principle is still, generate a PTAT and then use that PTAT to, add what do you call to the PTAT. You amplify it by an appropriate amount and add. So, here how do we generate the PTAT volt? I mean, how do you generate the band gap voltage? This current is PTAT. Now, how do we generate the band gap voltage? There are many ways of doing this, obviously. You can use one way of doing it. I mean, you can use any of those things that we've used in the past. So, let's say one way of doing this is to connect KR by 2 here, okay, and take the band gap output voltage there, right. So, that's one way of doing it, right, or you can take the band gap output voltage here. Other way of doing it is to take this all right, put KR there and VB1 there, So this will be your potential. That's one way of doing the band. All right. So one more variant, again using the same basic idea, is to say, well, this is VBE1, this is VBEN, this is R, alright. And what is the magic, what is the golden principle? To find the PTAT, the voltage across these two branches must be the same and the current must be the same. So at the equilibrium point, at the at the magic point, the voltage across both these branches is going to be same anyway, correct? So rather than use current sources, one could as well use resistors. So let's call this Rx, and I can go on. This is my, to push a current into these two nodes, I can use, remember that a large resistor is the same as a current source, right? The only problem is that the current typically will depend on this potential. You want, remember, both the currents must be exactly the same, alright. But then the argument you make is, well, when the circuit works, these two potentials are going to be the same anyway, alright. So I will keep varying this voltage, right, and keep looking for that magic voltage V, I don't know, I'm going to call this Vx star, where Va equals Vb, alright, okay. And at the magic voltage, when Va equal to Vb, this current is going to be exactly the same as this current, because the top terminal of the resistors are the same, and I am telling you that Va is equal to Vb, alright, okay. So what will we do here now? Now you I want you guys to help me figure out what I am going to do. What are we going to do? What plot will we draw? Vx on the horizontal axis, very good, okay. What about, pardon? We will draw Va and Vb, okay. So for Vx very small compared to Vx star, what comment can we make about Va? So when Vx is very small, what comment can you make about the current? The current will be very small. So on the in this branch, which voltage drop can you neglect? You can neglect the voltage drop across R. So for Vx very small compared to Vx star, which will be larger, Va or Vb? Yeah. So the same current is flowing through a diode which is size 1, whereas on the right side it is flowing through a diode with size n. So for so Va will be exponential, one logarithmic like that, okay, and okay, and for for Vx much smaller than Vx star, Vb will be smaller, right, okay, and as Vx keeps increasing, what will happen? Then it's logarithmic, then it will become do something like Okay. So, for Vx less than Vx star, Va is greater than Vb. So, what must you do? So, if so, in other words, if Va is greater than Vb, what must you do? Vx must be Va is greater than Vb. It means that Vx is less than Vx star. So, Vx must be increased, and vice versa. So, therefore, Vx is a voltage which is controlled by the difference between Va and Vb. So, it is a voltage controlled voltage source, and what must be the gain? Infinite. So, what must be the, this must be negative. Okay. Now, so what is this voltage therefore? What is the current flowing? Current always is Vt ln N by R. So, what is the voltage across this resistor? Vt ln N by R times Rx. Okay. So, what is the output voltage? Vb1 plus Rx by R Vt ln. Yeah. Supply voltage, where is it coming? Arey Baba, where? I mean, not just the circuit, any circuit that we have seen with the op amp, we have not connected, we have not drawn the supply and ground for the op amp. That's understood, right? Same thing here. Oh, I see. Okay, I see. Okay, okay. Yeah. I mean, remember, please remember that whenever everybody draws, anybody draws an op amp, it's understood that there is a VDD and a ground, right? Without it, nothing will work. Okay. Okay. So, if you want if you want kVt ln N, what will you make Rx? You make it Kr. So, then this will become kVt ln N, and the output will be kVt ln N, and this is Vbg. All right. Okay. And the advantage of this is that, what might be the advantage of this? I mean, okay, well, there's that is a very small thing, right? Now, you have no 2 extra transistors, but well, in the op amp you have like 500 million of them, so it really doesn't matter. All right. The nice thing here is that you're taking the output of the op amp, which is a, so if you connect a load here, if you go put RL here, what comment can you make about the output voltage? Will it change? The output impedance of the op amp is 0 anyway, ideally at least. So, this can tolerate, I mean, you can load it and the output voltage will not change. Whereas, for example, here, if you go and put a resistive load, what will happen? Yeah, current will be drawn from there and you will get messed up. So, I mean, this will need a buffer here, right, in order to drive some other thing. All right. So, that advantage is, that disadvantage is gone. Alright, so as I said, there's any number of ways of coming up with. I mean, the principle, of course, of the band gap is the same. All right, and is has been the same for a very long time, right? But you can see that the circuits look. I mean, we've seen, I don't know, at least what, 1, 2. Yeah, I mean, we've seen 2 ways of looking at the same circuit, right? And once you figure out the principle, you can. I mean, you can see that this variant looks very different from the op amp based variant, right? But the basic principle is the same. So you pump the same current. I mean, you can think of it as you pump the same current through a branch of size 1 and size n plus a resistor, and find when the voltage becomes the same, or apply the same voltage and measure the current and keep varying the voltage where the currents become the same. All right, and in either case, you will eventually end up with the circuits that you see, right? And these circuits actually very deceptive, right? So it's very easy to make a mistake, correct? If you don't understand, you will simply, I mean, if you write the equations, that the other circuit where you flip the mirror on the PMOS side and flip the mirror on the NMOS side looks, I mean, if you write the equations, they all are the same. So you would get tricked into believing that circuit works when it in reality does not. All right, and you've seen a similar situation earlier. What is that? Yeah, fixed GM bias also had the same problem, right? I mean, if you didn't know how the circuit came about, it's very easy to flip the other two. I mean, the mirror orientation, and then end up with a circuit that doesn't work. So yeah, that's all I had to say about band gaps, band gap references, and this just is a way of, I mean, this is just to give you a flavor of how op amps can be used for, I mean, to design lots of nifty little circuits, and it's not for nothing that the op amps are called the workhorse of analog engineering, right? So negative feedback is something that is an underlying. If you want to make anything work robustly, right? Negative feedback is an absolute must. Okay, and negative feedback is predicated. I mean, working properly is predicated on the fact that you have a high gain forward amplifier, right? And the high gain forward amplifier is basically an op amp. And now we not only know how to design the internals of an op amp, we know what those transistors inside are doing, but we also seen a use case of of an op amp in circuits that generate useful bias quantities. Okay, all right. So so with this, pretty much I think all the within quotes memoryless part of the course is over. All right. So the bottom line therefore is that however small the transistor gets, it still has inertia, right? Electrical inertia, if you want to think about it that way. And we need to now examine all the circuits that we have seen in this new light, right? So what happens to our standard op amps and transistors and stuff if I mean our op amps or common source amplifier, common drain amplifier, etc. What happens to all these circuits when the finite speed of the transistors is accounted for? So first we need to model the transistor when memory effects are concerned, and then replace the old small signal model we had with this modified one, and basically reanalyze all our circuits that we have done, and from there we go forward. All right. Okay.